I'm gonna start letting people in. All right, it's 9 a.m. Central Time. Good morning, everybody. Welcome to a new SPE GTTS Geothermal New Technology webinar. Today is really an exciting conversation with XGS Energy. Casal, thank you so much for the time. Thank you, everybody, for joining the call. I hope everybody enjoyed the topic today. I encourage everybody to post the questions in the chat. We'll have a Q&A 10 minutes at the end. So, Casal, pass it on to you. Enjoyed it. Thank you so much.
Thank you, Camilo. Can you hear me well?
Perfect.
Excellent. Hello, everybody. Thank you so much for joining this session. My name is Ghazal Izadi. I have a background in oil and gas. I spent decades in oil and gas and unconventional development in Baker Hughes. I had a focus around 3 years on decarbonization, energy transition, and geothermal back in time in Baker, and I was a global lead from the reservoir technical services for geothermal. I did my PhD around reservoir engineering, working both on geothermal and unconventional oil and gas. My first project around geothermal was back in 2009 to 2013, working on EGS projects and hydrothermal. Right after that, I came to the oil and gas segment and started to really work on these new technologies to unlock the unconventional shale and gas globally. Around a year ago, I came across XGS that has a very interesting approach in order to tackle the challenges around the geothermal for the scalability and the commercialization through material science. So I would like to share with you today what exactly we are doing and how the technology works and our go-to-market strategy. So looking forward to have the fruitful discussion with you. Just to make sure that we are not going to be interrupted with the network, I'm going to stop the video and looking forward to have this discussion with you. So I would like to a little bit talk about the problem statement in terms of the need for these carbon-free baseload power from where we are today to get to our goal to this net zero in 2015. If you look at the annual global electricity consumption, we are in a per hour type of range. And if we want to really look into to see how we can remove this gap with this carbon-free base power approach, we need around 15,000 terawatt hour per year. And having other alternative from the renewable side, like wind and solar, is great, but it's not going to really remove the problem statement from the picture if we want to reach this net zero. So what other alternative we have? I'm sure the audience here is very familiar with the legacy geothermal or hydrothermal system that we are placing a doublet system, injection and production well. And in some cases, we have enough pressure at the subsurface and the hot fluid or hot reservoir to extract the hot water to the surface and convert the heat to electricity or direct use. In some cases, we can see that after the pressure in the subsurface depleted, you need extra pressure through the injection water into the system. There are critical challenges here. First of all, the amount of water we need to pump in the system and the water scarcity issue as of today is a huge and important topic. Also, when we are dealing with the subsurface fractures, permeability, porosity, with time, the fracture could be scaled up with different mineral because we are dealing with this temperature, mechanical, hydraulic system that coupled in downhole, and also the other issue is around corrosion at the wellbore, and also the scale issue, not only within the reservoir but also on the production well. And because we are carrying and flowing a large volume of the water in the subsurface, in some cases we have the issue around the induced seismicity or subsidence, and some of other environmental issues like producing chemicals and gases at the surface. And these are all the risks that can be mitigated, but with going forward and talking about scalable projects globally, that we can compete with other energy solutions, I think we need to remove this risk from this picture to make sure that geothermal has the good space between other energy systems. So what we are showing here is that what we do not do. So how we do it. So XGS developed a technology in order to enhance the heat transfer from far field to the casing and the heat exchange between the rock and the working fluid. So we have the fully closed loop system. One single well, we don't need to have the precision of the horizontal drilling type of well architecture. So we want to have the well that the heat harvesting length of the well is placing in the right temperature gradient. So we go as deep as possible to get to the hot rock. Our innovation is around this thermally rich enhancement material, which we call it TRE. So we create this highly conductive network of thermally conductive material. We like to call it a squeeze process instead of hydraulic fracturing because these are very local. We are looking at single digit meter fractures or near wellbore damage around the casing. So this TRE material perform usually between 50 to 60 times more thermal conductive than native rocks. And what the difference between our solution and the EGS is that in the EGS and hydrothermal, you flow the fluid. We have a steady state of this material around the casing, and we only flow the heat. So when you place this material into the formation and near wellbore, this material become to the solidified state, and they just transfer the heat from far field to your wellbore. And the last piece is a fully closed loop. So you have a hot fluid return to the surface through the insulated inner tube. So we have a tube-in-tube solution. So that is how you are reducing the risk of the heat loss from the subsurface to the surface. So this is a concept that how the system works. So let's look at the performance a little bit. So as I mentioned, in a standard closed loop geothermal well, the energy output is fundamentally limited by two factors. One is the amount of surface area and contact from your wellbore to the hot rock, as well as the thermal properties of the rock, which in this case we call it thermal conductivity. So the way that XGS breaks this from this equation is we not only increase the surface area through our conductive material that we are placing around the casing to efficiently increase the heat transfer after we are circulating the working fluid, which is cold, and interact with the hot rock to extract the heat to the surface. Also, we are increasing the equivalent thermal conductivity through this material, which I mentioned is 50 to 60 higher than the native rock. So basically, we are creating this virtual wellbore in the subsurface without drilling larger wells in terms of length. I'm showing here a very simple closed loop analytical heat transfer formula, which the energy output at the surface has a function of thermal conductivity of the medium. Unit is watts per meter Kelvin. The surface area, as I mentioned, is the well length or heat harvesting length and the hole radius. Temperature drawdown, which is the temperature difference between the resource and the working fluid, and also some of the specific properties of the rock, like a specific mass and a specific heat. We're just playing with the variables in this analytical solution here, and you can see by only changing two variables, increasing the equivalent thermal conductivity through TRE material and the wellbore radius, because you access to the higher volume of the rock through our TRE material that reach into the formation, we can improve the thermal performance by 100% compared to other closed loop without TRE imposed to the subsurface. So we did not only look at from the analytical model, but we developed this hybrid thermal and power modeling approach that we are coupling finite element method to understand the heat transfer mechanism, fully based physics approach. There is another component that we need to understand when you understand the heat transfer in the rock through our TRE material. Then we need to model the heat exchange process from our casing to the working fluid. So we did a lot of simulation and modeling through the computational fluid dynamic tools. These are commercial tools like ANSYS and Abacus. And from the learning on the physics-based simulations, we also developed a couple verbal model in-house that we can really do the sensitivity analysis and tailor an engineering design for how we need to place the TRE in the subsurface, what type of property we need based on the subsurface condition in terms of geological properties. So those type of approach has been carried on fundamentally to understand what's going on. And most of the simulation I'm showing you follow this workflow. So let's look to see that how TRE works. I'm showing here the two cases at the top, which we don't using TRE and around the casing. So you can look at the map view of your wellbore. The middle pictures are showing the temperature map of the wellbore after 5 years of production. And we also not only look at the temperature profile or transient analysis, but also the heat flux at the wellbore. So through the theory material, we not only have access to 30%, in this case, more hot rock. So the delta T here between the working fluid and the resource temperature is around 200 C. So we injected 50 C fluid to the 250 C rock. So when you start to extract the heat from the resource, you can see that with no theory and only having the closed loop, you have a limited amount of access to the hot resource downhole. And the heat flux is very important for us because we would like to know that what type of configuration of this material needs to be intact with your casing. And heat flux is not only telling you that how much heat is flowing far field to your casing, but also what is the rate and the velocity and the volume of this heat transfer to your wellbore. I would like to show you this heat transfer analysis for these both cases. These are the animation that we are showing. Case on the left showing the theory placed around the casing and no theory in the subsurface. So you can see that how much you have access to one single stage theory that's bringing the heat far field to your casing and working fluid. So this drainage mechanism is very important for us to know that how far we need to go from wellbore and how to place it at different depth and different temperature gradient. So this is a very important topic for us to simulate the heat transfer with time and see that how do we need to place and design our theory material for the subsurface. So as I mentioned, we have done a lot of modeling to really understand the physics and the base of this work, but we wanted to validate and calibrate our models. So that is why we built this high temperature laboratory in France that we can simulate the subsurface with high temperature basically condition to understand how our material works and what is and how we can basically validate our simulation, numerical simulation. So what you see here, this is the high temperature oven we are showing. We can reach to 400 degree centigrade rock temperature. We have done a lot of monitoring in order to understand how the whole system works. In the oven, you can see on the right that we put the column of the granitic rock and placing our theory material in between. The sample size is 1 meter. We have the inner tube between the samples that we build a closed loop basically process here. So you inject the cold fluid from the downside of the tube, outside of the oven. The fluid heats up and go out of the oven from the top. 140 sensors placed in this setup in order to measure and monitor the heat drainage and heat flow on the granite, on the theory material inside and outside the tube, and also the inlet and outlet water temperature. And these are all the work has been done to make sure that we have enough empirical data to calibrate and validate our model. So this is, we really like this lab because we can play with the temperature. We can really go up to 400 C. We have done a lot of tests at different temperature, different configuration. I am showing a case that we ran a 250 C temperature test. What we are showing here, you can see the temperature profile versus time and amount of heat that you can extract from the granite versus the theory. So as I mentioned, rock is a very lazy element. So at some point, the granitic rock with 3 to 5 watts per meter Kelvin thermal conductivity cannot bring the heat to the casing, and we can really simulated both in the lab demonstration and our simulation that amount of heat that granitic rock can draw, and transfer is very limited. Through the TRE material, we can draw 50% more in this case, and that scale. So, and we also see that there is a very good match between the numerical results and predicted experiment results. So in the best case scenario that we run in a higher temperature and with certain configuration of this TRE material between the samples, the heat recovery increase was up to 90% compared to the case with no TRE. So, so how does it work? So we have this key innovation around heat harvesting process to generate heat at the surface. Based on the resource condition in terms of the temperature and the geological setting, we expect to get around 3 to 9 megawatts thermal power from each single well. The way that we look at the overall field development strategy is that how many wells per pad and how much megawatt thermal we can generate at the surface. There is no innovation around electricity generation or transmission. We are going to use the standard off-the-shelf steam turbine or ORC for the lower temperature to convert the heat to electric power. But basically, most of the work that we are doing is in order to how to optimize our well path to maximize the thermal output for certain geological setting that we need to deploy our technology. So the technology is very, very interesting. Let's look at economics. When you look at a level of cost of energy or electricity, looking at alternative solution from the renewable world or either gas combined cycle or gas picking. So you can see that comparing the overall LCOE, dollar per megawatt hour, we are really looking at a very lucrative numbers, both in our brownfield projects or greenfield. So brownfield is basically we are repurposing the geothermal well, which is running dry, and we can deploy our technology into the well, which is not working anymore, and start to extract the heat. It is very economically interesting because all the surface facility is ready to bring this dry well back to life. On the greenfield, when we are looking at drilling the new wells, and then we need to have the surface unit in place and all the interconnection and the grid. So we are really competitive with other alternative solutions in the market in terms of LCOE and the cost for these projects. So in terms of availability and the market for this technology is huge. So we are showing the map from the Clean Air Task Force that they look at and map different resource temperature and depth. So we are showing here that if we need to access to the hot rock globally, you can see all the shaded purple section on the map are the sweet spot for our technology. So it's not geographically dependent because we don't need the hot water reservoir. We don't need the permeability porosity. We just need to go after heat. So that is not only impact on our scalability faster, but also it's really reduced the risk and cost of exploration, because with a very simple geothermal or heat mapping through the simple logging tools to understand at what depth we see the temperature is getting to the sweet spot, which we would like to have minimum 200 centigrade temperature for the technology to make it economically viable. And you can see there is so many places around this world that we can deploy the technology today. So I love all the geothermal solution and the systems that we are developing around the globe. But when it comes to scalability, I think there are certain and key parameters that we need to consider. and that is why we believe XGS can play a significant role in this market. In terms of energy output, so as I mentioned, we use this material that conduct 50 times more heat, thermal energy or heat from the rock and to bring it to the casing. And this is really important to maximize the energy output long term. The low risk of project development, I mentioned that we don't really need expensive and risky exploration phase. We are not going to have any dry well because we can deploy this technology in any geographic condition as long as we have heat. It's not dependent to the water. So when you look at today amount of water they are injecting to the very good steam field compared to what we need in terms of water requirement. For the whole system, we require amount of water that it exists in your swimming pool for single well compared to 1 million gallons of water that needs to be injected in the other system. And we are going to use this water over and over. Our water is in the fully closed loop, so there is no OPEX related, so we are not going to have any corrosion on a scale issue that ultimately impact on the project OPEX. So by looking at removing all of these challenges, as I mentioned in the first slide, so we really think that the scalability is much more easier through XGS technology and approach. So as you know, we are going also to benefit from continuous industry advancement in terms of reaching and accessing to the higher temperature rock faster and more efficient, from the drilling technology, from the drill bits technology that is coming from both oil and gas and the geothermal startups that going to really drive these technologies to make it much more cost efficient to access higher temperature resource. So these are the complementary technology for us, and we are working with most of these startup and innovator to make sure that how we can make our economics even better as what we have today. So where we are in terms of roadmap, up to this year, we have done a lot of work, proof of concept, early testing of our material, thermal modeling, and how this material works. We build and demonstrate at a meter scale, high temperature in the lab to get the empirical data and validate our thermal models. We are in the planning of the shallow demonstration in Texas to place this material into the subsurface, and this is the first time we are going to interact with oil field equipments. So hopefully by end of this year, we have all these milestones accomplished. We have planned to enter to a brownfield and a dry geothermal well to have a full installment of integrated system in Q1 of 2024. We are planning on selecting the right well for this project. Most likely it will be in California. So what the prototype well look like is that the well is already drilled, the well is dry. So we are going to enter the well, we are going to placing our theory material and then casing and the return tube and then produce heat at the surface. So the reason that we think that this is a step change for the company is that because we would like to, after this prototype well and everything is tested in one single well at the right geothermal condition, we can really accelerate our commercial project for the other fields, both brownfield and greenfield. I would like to brag a little bit around our team and our board of directors. We have one foot in Silicon Valley through our chairman and board from former chairman and CEO of Intel, as well as one foot in oil patch from the former chairman and CEO of Baker Hughes, Martin Craighead, and having a really diverse board from Saudi Arabia, Dr. Khalid Al-Sulayem, from Secretary of Navy Ray Mabus, and also our founder, Dr. Pierre Moncars, who is an adjunct professor from Stanford. So the board is really working fantastically with us to make sure that we have the right path for the commercialization and scale up. And also our leadership team from our CEO, Josh Brewer, who has a lot of experience to really scale up the startup, as well as our technical team who are both sitting in Palo Alto and Houston. So our headquarters located in California, Palo Alto, and we have all our technical team sitting in Houston. And also, we are so lucky to have the right partner and investor, especially Anzu Partners. So I think we are very fortunate to working with this level caliber of people and right partners around us. I would like to pause here. This was a little story about what we are doing and who we are, and I would like to hear your feedback and answer questions if there is any.
Are you in the...
Ghazal, thank you so much for the presentations. Yes, we got a few questions from the group, so I think you answered a few of them, but I'm gonna just go one by one. So the first one is the lab in France an independent R&D company?
So yes, this is our laboratory that as I mentioned, our SVP of technology, Dr. Axel Bois, who was running this company Curistec. This laboratory was the purpose of this lab is to bring a lot of material science and operation for the oil and gas testing. So we had a lot of equipments ready in this lab, and also we enhanced it with this high temperature equipment. So this is basically a part of XGS laboratory. So it's not external lab.
Perfect. Thank you, Ghazal. The next question is, can you elaborate a little bit further on the difference between fracking and natural fractures? What is really the ideal situation, and how do you manage that difference between induced fractures and natural fractures?
Yes. So as I mentioned, in so many cases, when we studied in terms of the placing of this material around the wellbore, we don't need to reach to the reservoir. So as I mentioned, these are less than 1 meter fracture length that we are looking at. It's important to be how to place it and what type of configuration we are creating in the subsurface. But just comparing with what we are trying to do versus the hydraulic fracturing, we are talking about geometry about 10 meters versus 100 meters in the oil and gas unconventionals. In terms of volume, we are very, very low volume that we are placing. The pressure is very low to create it. So these are really, we call it near wellbore damage to place this material, and then we squeeze the material with very small pumping units that basically we are using at cement job. We don't need this frac fleet to create those type of system and surface area downhole. In terms of how we are interacting with the natural fractures, so we have different setting at this igneous rock, right? Either it's very low porosity and permeability, but most of the case we don't rely on that. So if we have a natural fractures connected to our wellbore, it's a plus. So we can squeeze this material into the fractures around the wellbore and leverage this heat harvesting length through these natural fractures. But yeah, so that is a distinct difference. And the reason that I said it's very environmentally safe, because as long as this material plays into the fracture, it becomes solidified, because the fluid squeezes out when your rock started to compress. So this material is staying in the solid state into the fracture, so you really don't flow anything in the subsurface. So that is how we think that we reduce the risk of induced seismicity with this process, that we solidify this material into the fracture and basically cement the fracture through our highly conductive material.
Perfect. So that was a very well detailed answer. So the next question is about one of your slides. You were explaining the TRE treatment, but the question is, how do you seal off the casing after the TRE treatment?
So I think that we place the theory material and then we put a casing, and we, instead of cement, we use another formula as a theory sheet, we call it, which is working as a material between the casing and the theory formation. So we are not going to use any cement job in this work. So everything around the casing and the formation will be through our thermally conductive material, but different recipe and formula.
Perfect, Hassan. There is another question around environmental considerations when injecting the TRE material. What are kind of the critical environmental considerations?
So the TRE material is composing of water and some very green additives, and the solid part is coming from some carbon-based organic natural occurring minerals. So we don't see any issue around the environmental permitting for this material, because this material is very safe. They are not degrade with temperature, and we believe that in terms of the environmental permitting of this material downhole, we may not have any issue, because these are the organic natural minerals that we are going to use.
Thank you, Hassan. So one of the questions is, okay, it's 3 to 9 megawatts. What are the boundary conditions for this from a power generation standpoint? Is the length, is the OD of the wellbore, is the kind of delta T in the environment? What is the real boundary for the system?
I think everything impact on the thermal output. The way that we look at it is the main important part is the temperature gradient. So and how deep we need to go. So the well construction and the well capex is one component, and how much we extract the heat because of the temperature of the resource is another component. In terms of how we are looking at the project economics, is that absolutely we look at the capex part of the business, but also how we can convert the heat to electricity. So based on the temperature we get at the surface, pressure and rate, we need to select the right setup in terms of a steam turbine, single flash, double flash, triple flash, or ORC. And then you have the thermal conversion. And then we also included some of this decline that we see from the past in the geothermal well, as well as a lot of simulation we have done in order to make sure that how we can bump up the thermal output and reduce this decline through our material, because that is really dictates the economics long term.
Thank you, Sal. There's an interesting question about re-entry wells. So in that particular scenario, the casing is already cemented. So how much does that particular fact in terms of heat transfer reduction or heat transfer design?
So when I talked about brownfield, I specifically addressed geothermal brownfield, and 90% of the geothermal wells are open hole because they want to have flow. When we are looking at oil and gas, it's a little bit different, but we believe that there is other options, that if the wells is in the right temperature gradient, we may need to do the sidetrack because my experience to look at oil and gas wells to repurpose it for geothermal, there might be a lot of challenges. Yes, casing, cement, corrosion. Sometimes the recompletion of the well, it makes more, it's much more costly than have a sidetrack if we believe that the well is in the right geologic formation and temperature level. So that we have a lot of idea around oil and gas, but again, oil and gas is a different well structure in terms of diameter, in terms of the completion, and stimulation has happened. So we need to have a different screening scenario in comparing geothermal versus oil and gas wells.
Thank you, Sal. I think that's a really interesting clarification. There's another question about the low profile insulation system that is needed in the tubing. Can you provide a little bit more insights on how to really understand the isolation and what is really the strategy?
Yes, I think there is a lot of a use case around this insulated tubing for offshore, specifically to reduce these paraffin issues. So that technology is very well understood for those type of application. I agree, because we are looking at different well design in terms of diameter and efficiency long term, because we have a little bit different environment compared to offshore oil and gas. that is why we are working with our vendors to really engineering those technology to adopt it. It's not innovation, it's more adoption and engineering side for that type of that part of the system that we try to bring into the geothermal well.
Thank you, Ghazal. Another question: what is really the flow rate kind of windows that we are looking at for the system? Is low flow rates, high flow rates?
I think the flow rate, it's if you look at from the well by well, it's very different than when you do the field management, right? Because at the end of the day, we would like to have the certain volume and at a certain temperature to flow into your surface design setup, either steam turbine or ORC. The interesting thing about flow rate is the parameter, operational parameter, that we can play with, either increasing the rate at the early time of the project because we are not going to see any thermal decline, and then reduce it longer term because you want to make sure that the well reheat again. So playing with the rate in the field level, multiple well is one of the optimization process that we are carrying in to see that what is the optimal rate at what time of the project development that we want to have to maximize the thermal output at the surface.
Thank you, Ghazal. Another question: we say that silver would be the very best conductive material to use for conductive heat transfer in fractures.
So we are not going to use any metal as a thermal conductive material, but that is a very good example to say that we are having a thermal conductive material between 160 to 500 watts per meter Kelvin through this naturally occurring material that we have. This is basically our IP and our innovation in this domain, to make sure that not only we have the right thermal properties of this material, but we can mix it, we can pump it downhole. So there was a lot of work has been done through our testing and mixing to see that we can deliver this material downhole and it perform as we expect. And one thing I want to highlight here, that this material, the thermal conductivity of this material increasing exponentially under stress and pressure in the subsurface, because when the material compacted, the thermal conductivity increased, and the subsurface condition at that level at depth, we have enough compressive strength and axial stress that can compact this material to reach to that thermal conductivity that we are seeking for our well performance.
That makes sense. Thank you, Ghazal. Another question: could the TRE be applied to a radiator loop, closed loop system rather than a pipe on pipe?
Absolutely. I think any geothermal well can leverage our material, because what we try to do is to make sure that we are creating this virtual heat exchanger through material instead of the mechanical heat exchanger, and this act as a radiator to bring the heat to your casing. Either it's U-loop well, or is it a coaxial, or any type of well. We can engineer and design this material to bring the heat back to your well much more efficiently.
Perfect. Thank you, Ghazal. Here's another question around basically what are the downsides from thermal behavior with the high conductivity materials over time in terms of risk for the well?
So I think we have done a lot of work in order to understand that what are the critical risks for us. As long as we place the well safely into the hot rock in the right condition and the efficient cost, I think we really remove that part. In terms of the risk, we might have some risk around the return tube long term, right? So that is why we really carefully analyze and engineering that system, because we want to have the consistent performance long term through our insulated tubing. And there are different solutions in the market that may work short term or long term, but we don't see it as a critical risk, because I think this is a more engineering challenge that we can solve it. In terms of placing this material in the subsurface, because we are not going to have any flow, as I mentioned, so we don't have any risk of other system. So because we are not going to interact our water with the rock, so we don't have any corrosion around the casing. So we have a very system that we are not worried about some of the production challenge we see from oil and gas or other geothermal system, because we don't rely on the fracture system. We don't care about the permeability change. In brownfield, yes, we don't want to change the permeability because there is other operation well, and they're producing from the steam. So that is why it needs a little bit different geological evaluation to make sure that we don't perturb the stress and pressure from the wells that are already producing. Because even though the permeability process doesn't matter for our well, but in the brownfield, we need to be a little bit more careful about how we are dealing with placing these wells. But at the end of the day, this is the lowest footprint and lowest risk technology that I can see in the market, because we are not relying on geology. We are not going to have any OPEX long term. We need to make sure that we place this material in the right way and the right thermal conductivity to extract the heat the most efficient way.
Thank you, Ghazal. Next question is around technology combination or integration, power generation, cooling and heating. What is the target for XGS?
So it depends on the market and it depends on the economics. So I think in the Western US, we definitely would like to develop these power projects because the resource is fantastic. The ITC is helping us to really reduce this project's cost and make this project more commercial viable and faster in the market. I think if the resource, we are also looking and talking with a lot of our partners in order how we convert this heat to other application. As I mentioned, one of our investor from our cap table is coming from Saudi Arabia. So Saudi is a very high temperature resource around the Red Sea, and I think there is so many other applications for desalination that we can use the heat from these wells and the power as well as power. So this basically co-production approach based on the resource temperature and what we want to achieve in different geo market is very important to consider. And also Asia Pacific, which is another interesting region that the hydrothermal is very good, but we see that they have a lot of challenge around geothermal geofluid like brine. They have a lot of issue around corrosion, scaling, the fracture permeability is getting close, but the heat is there. So how we can access to this heat and convert the heat to electricity, which less cost and more efficient way. That is why they are very interested in XGS technology.
Thank you, Ghazal. There's a question here that I skip over. So if the pipe and pipe a thermosiphon, or does it require a pump, either at the surface or downhole?
Yeah, that's a very good question, because we want to have this pressurized system because we don't want to have multi-phase flow in the wellbore, especially at the surface when we are extracting the heat through our working fluid water. So this would be always a pressurized system. So we only have a single flow and the hot water at the surface in order to go to our either heat exchanger or some other pressurized system before it goes to the steam turbine.
Thank you, Ghazal. There are kind of three questions related with the same topic in terms of working fluids. Any considerations for additional working fluids down the line?
Absolutely. I think we are constantly looking at alternative working fluid to see that if there is any advantage, not only from the thermal performance. We really look at it from the both sides, the technical and the project economics. So this is something that we are working on it and try to simulate it and see that how it works and what is the best scenario. But for the next few wells, we definitely use water to really understand how the system works. But the alternative fluid in order to improve the performance and also reduce the cost is much in our technical roadmap to study and test in the next future wells.
Thank you, Ghazal. This is a clarificatory question. So is there any kind of losses, water losses in the closed loop system? And if so, what are that percentage that you guys assume from an OPEX standpoint? You mentioned that there is not really a lot of water required compared with traditional geothermal, but what are the losses in the system and how do you factor that into the OPEX?
So if we compare the overall closed loop concept with our concept, we are fully closed loop. It means that we have a casing full in place. We are going to have a tube-in-tube, isolated return tube. So we are not expecting, and because we also have the pressurized system, we are not going to flash the water. So it's not going to steam mode. So we are going to use the same water. We don't see any risk on the loss of the water in this system.
Thank you, Ghazal. So when you pump your material, are you exceeding the frac pressure, or what is that relationship between the pumping pressure and the fracture gradient?
Yes, I think definitely, because we would like to create these local fractures, we definitely needs to go above the fracture gradient, right? But when you look at the amount of pressure and the volume that we are placing near the wellbore, it's really minimal. We are talking about less than a few hundred barrels of the TRE fluid around the casing. We just need to make sure that we don't need to create a long fracture to really change the pressure, to use the very high pressure units at the surface, like hydraulic fracturing, basically. So we can use it with a very low light cement unit to pump this material near the wellbore.
Thank you, Ghazal. There is a question around thermal conductivity for the steel, traditional or normal steel and the TRE, but isn't it the steel casing the limiting factor for the heat production?
Yeah, I think that is a very good point, and we look at it from the from this type. If we change the casing thermal properties with other alternative material, yes, I think it can be a little bit like damping the flow, because it has a different thermal conductivity our material. By most of the consideration we did in terms of the modeling and the lab test, we assume that this is what we have in terms of the availability today in the market. It's much more standard to get it in terms of supply chain and procurement process. There is some downside, but most of our analysis is based on the properties of the casing still that we have today. But we are talking with other tubular vendors that is there other alternative for us, which is much lower weight, as well as the higher thermal conductivity that we can replace in the future.
Sal, the last question, are you going to be attending Geothermal Rising Conference?
We are super excited to be there, and we have a booth this year over there. So I really encourage you guys to come over, and we would really like to see you there and continue the chat. So, and I really appreciate to being here today, and very excellent question that came up. Looking forward to make this work with all of you helping us to be successful to make the geothermal viable. So thank you so much.
Thank you, Ghazal, for your time today. Great presentation. Thank you, everybody. I look forward to seeing everybody in the next technology webinar. Have a good one. Thank you.
Thank you.